And now for science. Batman, better approach to mobile ad hoc networking. New routing algorithm and daemon for wireless community networks. We have developers for mesh networks from Freifunk Berlin. It's Elektra Wagenrath and Axel Neumann. Please give them a hand. Thank you.
Well, I have to correct this. This is not Axel, like some people here in the room may know. It's Marek Lindner. Axel couldn't come here. I hope I don't bore you. In the beginning, we'll just do a little introduction into ad hoc networking. Next slide, please. Well, I hope I don't bore so many people here in the room, but I'll just mention it. If you use Wi-Fi, usually you use the infrastructure network. The symbol here is the red dot. You have some access point, and you connect as a client to the access point. If the access point fails, the network is down, nobody can communicate. In ad hoc modus, in Windows they call it peer-to-peer mode. All nodes can connect to each other directly. They call it peer-to-peer networking, you know, in Windows. We call it ad hoc. Okay, next. With ad hoc, because every node can connect to each other, another term is multi-point to multi-point networking. It's possible to expand the range of wireless coverage. Here in this slide you can see that A is in the range of B, B is in the range of A, but D is not in the range of A anymore. So if you apply routing, so if packages are forwarded from A to B, from B to C, from C to D, you can expand the range of wireless to a very great degree. Next slide, please. Well, so it's possible to do multi-hop routes. Here you can see the disadvantage if you use an access point network. A and B and C, A and B can communicate. If C could communicate with D, D could communicate with B, all would be connected, but if it's just an access point network, you have no connectivity. And another big disadvantage is if D and B would be clients of that access point, they may have a very good wireless link between D and B directly, but they cannot use it because they're clients, so they have to send their data to the access point and back to B, and so the bandwidth is maximum half of a single link. Okay? So, well, this talk is about routing protocols for ad hoc networks. They could be mobile, but in our case, usually we have mostly static setups. We have wireless nodes on rooftops, or some people start their laptops and connect to those devices on the rooftops. But our protocol could be also used for mobile applications. I would say there are, well, there's okay. I guess you should check out the weather report now online. There are several categories of routing protocols for ad hoc networks. I'm not mentioning all of them. There is source routing, which is reactive. Distance vector routing, which is proactive. Link state routing, that is also proactive. And Batman, which doesn't really fit in one of these categories. Some people say, well, Batman, it's just another distance vector algorithm, but you'll have to decide in the end. Next slide. Well, I hope I don't bore many people here. Source routing is a very old approach that it was in theory used or suggested for mesh networks. Source routing means you start your node and you have no clue who is out there. If you know, okay, there might be a node X somewhere, you start asking the network for a route to X. Next slide, please. So A wants to communicate with X, it needs a route. So it starts flooding the network with a route request. And well, this route request is forwarded through the network. In the end, finally, it will terminate at X. Next slide. X will send a route reply back. And the package that is forwarded and is floating back lists all the nodes that were on the way. So in the end, A thinks it has a path to X. In theory, this should work. It should be loop-free because if there is a routing loop, if one of those nodes occurs in the routing more than one time, there's obviously something wrong and you got a loop. But the problem is that the end of the route is deciding about the path. And just do a quick flooding and waiting for the first reply, it may give you a very bad route. If you use source routing like this, which is purely reactive, you will get a miserable route at best. By chance, you get a good route, but it's not very likely. Well, I'm just only striving distance vector algorithms. It's a proactive algorithm. The links here have metrics that could be measured, that could be given in by the operators. And the nodes are flooding their whole routing table, or a distance vector table, and they're all trying to sync these tables. Next slide, please. This causes lots of traffic. It is very slow responding to changes. There are some really funny problems in the algorithm, like a count to infinity problem, and the problem that bad news travels slow. So you may believe there is a very good route, but it doesn't exist anymore, and it takes a long time to learn. And if you depend on a node giving you a package telling you, hey, this doesn't work anymore, but this node is not accessible anymore, you'll never learn that it doesn't work, and you still believe in that route. So it's not really useful. So we come now to link state routing. Link state routing is now, I think, most popular in mesh networks. We at Freifunk, we were working on OLSR. OLSR is the abbreviation for optimized link state routing. We're just striving this again. In link state routing, node A sends hello messages. They are link local. It says, hello, I'm here. Somebody out there. B does the same. So A receives hello messages from B and knows, oh, B is a neighbor. B receives messages from A. Ah, I get a neighbor, which is A. And A will then send a package to the world saying, hey, I'm A. I have only one neighbor, it's B. And this message is flooded over the network. We got more people in the audience since it starts to rain. Very good. Well, there's not much to say to this slide. It's just the way it is flooded. Next. The information about the topology of each and every node, saying, I'm C, I have neighbors B and D. I'm B, I have neighbors A, C, and D, is collected by each and every node. They create a database, and they use the shortest path algorithm of Etzker, Wilbe, Dijkstra to calculate the shortest path. Next. Well, before I start talking about Madman, I have to explain why I think that this link state routing approach sucks. The routing protocol, and OLSR, or any other link state routing protocols, they are calculating the route from one node to all other nodes in the network. And they are calculating the full route. That means they have an idea. Sometimes we have routes with 22 hops in our wireless network. And so they're calculating routes of 22 hops. But the picture of the world that they have is never synchronized over the network. Because if I'm 10 hops away from another node, the topology information that I get only comes very seldomly, and it may take a long time. So the information I have is most of the time completely inaccurate, But based on this inaccurate information, I calculate a long route, and then all I can decide is which of my single hop neighbors do I give the package, and then I trust in this neighbor to do what I think he's going to do. And so with all other nodes in the network. I hope I'm not way over your head. Do you have questions at this point? Can somebody go with a microphone to this guy? Or just wait, it's hard to get your...
I mean, I just wonder about the possibility to use GPS to locate the spots, but maybe this question does not... at the wrong point of time in the talk.
Okay, GPS you mentioned. I omitted geographical routing approaches in MANETs or in mobile ad hoc networks because you need extra hardware or you have to manually enter your location. And it could be, we are very near, but between us could be a steel building. So we are very near, and so I should route to him, but actually there is absolutely no chance to communicate with him. So it's no use. It could be for shortwave and military applications in the lower VHF bands, it could be useful because they have relatively long shots, because they have relatively long range, so there a geographical approach could be useful. So, to sum this up, OLSR is calculating like hell, and it takes lots of CPU, and they're calculating informations that are absolutely not useful, and sometimes they cause routing loops because one node thinks, there is some hop far away, but this hop will give me perfect connectivity to some other node, but other nodes know better. So I send it there, but others send it back because they think the best way is going over me, so we have ping-pong effects, or small routing loops with 3 or 4 nodes. And still these funny problems, even though we improved OLSR to a big degree, still sometimes we have routing loops. So we thought, okay, we need a better algorithm. And we had the idea of Batman. The difference between the other protocols is they either search for routes or they calculate routes. Batman does neither search for routes, neither does it calculate routes. It's only detecting routes. We're just flooding the network with small packages. We call them originator messages. In the next slides, we're going to follow the path of such an originator message. In the beginning, A is creating a message saying, hello, I'm A. I do exist. This is my first message to the world. It sends a broadcast. This broadcast is received by those 2 adjacent nodes, and they see, there is a new package from A, or they may see, there is A, and I receive a package. And they will see by the sequence number of that message, I received that message for the first time. So it's necessary to flood the network with this package. So both nodes are repeating it. Next. Well, so the next one will receive it, or even more nodes will receive it. Some packages are getting lost, so this one is lost. Sometimes this link will work, sometimes the package comes through, sometimes it doesn't. And the same goes to queue. Next. So, but in the end, H gets the message, broadcasts it, and so the other 2 nodes that missed the package will now get it. Next. And finally, it will come to X. And X will see, I received a package from A over W. Next. So it will do a very simple thing. It will do a statistics saying, I learned about A, I received it from W, it was the first package, so there's one in the list. So we just watched one single package. A continues to send packages, and they will follow their way accidentally through this network. On paths where we have good links, the likelihood of getting through is bigger. On paths where there is lots of interference or nodes have a high CPU load, they won't be processed too fast, so they will take longer time or get lost. And X will just look who is giving me a given sequence number the first time and do a statistics. And so it will see, okay, I have 4 neighbors. Those 4 neighbors give me packages from A, and it will just look, okay, this is the best neighbor to that destination, and just choose the next neighbor to forward its packages if it wants to communicate with A. That's it. It's very simple, very primitive. Note that it's the version 1 of the algorithm. It has one major design flaw. It thinks if a package comes from a direction, it's also the best way to send the package to. This could be wrong in wireless networks because sometimes links are not symmetrical. They may work 100% from Marek to me, but 0% from me to Marek. Next slide. So we knew from the beginning that it is a design flaw, but we had the idea of this algorithm and people said, well, that sounds simple, sounds fantastic, but do you really think this works? And so we did an implementation to see it works, and then we added bidirectional link check, so to make sure that if I receive packages from Marek, I'll check if he can actually receive me too, and then I'll accept the packages that he is forwarding. Next. So I'm almost at the end of my part of the presentation. There is an ongoing evolution. The basic principle is set since version 1, and we made some improvements. One big improvement was that we had a bug in the algorithm, but it would be too hard to explain at the moment. I think it's not the right point here at the presentation. But now in the implementation, we have multiple interface support. We are connecting to internet gateways via UDP tunnels. So actually, a Batman client, a gateway client, can say, I want to have this gateway and not another one, which is a major problem at the moment in OLSR, because the network may think, the best gateway for this node is there, and then it changes its opinion and says, oh no, it's there. Oh no, it's there again. And all the time your stateful connections break down. Your SSA session breaks down, you're kicked out of IRC. And we thought, hey, we have to get rid of this. So I'm the client, I decide this is my gateway, and no matter how the routing algorithm routes my packages through the network, they will terminate at my gateway, and there will be no flipping of the gateways. Yeah, of course, there was some improvement in the scalability, and I think it's now the right time for Marek to take over. Thank you very much. Well, Marek reminded me it's now the right time to ask some final questions because I will be off the stage. Well, almost.
Just curiosity, is this ad hoc connection using some hopping from the nodes, or in your design you should have more wireless cards? I mean, there is no possibility to be connected on the same time on different nodes, right?
Sorry, I didn't get it.
I mean, if you have an ad hoc connection.
Ad hoc?
I mean.
Ad hoc.
Ad hoc. Okay.
Oh, sorry.
This will be only with one other node at a time, and then you have to hop.
You mean the routing is only using one route at a time? No?
I mean, if it's going to hop, I mean, you are using one wireless card.
One wireless?
Card.
Card, yes.
Yes.
Not necessarily. You can set up a node with 4, 5, 6, 8 wireless cards, and you can enable Batman to run on 8 interfaces. So it will look on different channels if you configure the wireless cards.
Okay, well,
accordingly.
the question was just if it's working also with one.
Yes, yes.
Okay.
Basically, our networks operate most of the time with one wireless interface in the device because it's cheap. We're running inexpensive networks that people easily can join. They have just to invest maybe 30 or 60 euros to purchase such a device.
Yes, yes, of course, but you don't have performance problems.
Of course, it would be even more interesting and powerful to have super nodes with at least 4 interfaces per device. That would be great.
Okay, thank you.
We'll get there.
Question. Do I understand it correctly that this...
Louder, please.
Do I understand it correctly that this routing algorithm still stores the routes to every other node in the network in every node's memory?
The routing algorithm is proactive in the way that it populates the routing table. It's not calculating routes, but it will detect that there is a route and it will put the next single hop neighbor as a router or gateway to the destination. So in that case, it's proactive.
But it does have a list, but every node has a list of every other, with every other node in the network?
Yes.
Okay.
Yes, it will see that there are many other nodes by detecting their originator messages. Yes. And I like this because I like to know how big the network is and how many nodes there are that I can communicate with. There's another question, please.
I wonder what's being used as a route release mechanism. When a route exists, how do you release a route after it's been set up but it's not working anymore? How are routes deleted?
How routes are deleted?
Yes.
Oh, that's a very interesting point. But I think this is mostly the part of Marek. Batman is opportunistic in deleting routes. That's a very important thing. One node is occurring to me once. So if I don't see an alternative route to that node that is better, then for a long time I stick to that route, because having a route that doesn't work anymore because that router is no longer accessible at all is better than deleting a route to a node that is actually existing, but I just deleted the route. So Batman is opportunistic in this, and there's a purge interval. At the moment, I modified it to several minutes. So if I don't hear anything from you for a few minutes, I will start deleting it. So there's a timeout. But the timeout is very, very long, because we like to have a route that may not work because you're no longer accessible, then having the opposite way, having no route to somebody that is accessible. Okay? This other question?
At the moment, I think you just implemented a delay-based routing protocol. And what I think of is when you find a route to some destination and you use this route for a lot of traffic, the delay will increase. And so when the next OMG is coming, you will find another route. And think, oh, now this route has the lowest delay, and you will switch over to this route. And next time the next OMG message comes in, you will also switch back, because you have this oscillation problem with delay-based routing. And I cannot see how you will avoid this in your protocol.
Hast du das komplett verstanden?
The problem is not so big as you might think. We have internal statistics, and you described the problem if we have 10 packets from neighbor A and 10 packets from neighbor B, and then we get 1 packet from A, and later we get 2 packets from B. Yeah, that's what you mean, some kind of hopping, of route hopping. Is that what you mean? Maybe we give him back here the mic.
Yes, okay.
Just to clarify the problem, I'm not quite sure that I understand it correctly. Yeah, it's not so problematic. At the moment, one neighbor has to have more packets than the other neighbor. In rare situations, you may have the switching, but we have an internal opportunistic measurement to not change too quickly and too often.
There is a slight hysteresis, but even if the algorithm switches quite often, there will be no packet lost. I have seen it switching. I've forced some situation where it switched very often, and there is no packet lost, only if the wireless layer doesn't work. The acoustics are miserable here. Okay. Yeah. We are going later into this with more detail. So I think we have many questions now, but we will have to proceed with the presentation. And afterwards, we'll use all the time that we have until we're kicked out to answer them. And later in the wireless village. Okay, just final question.
So in this scheme, you have each node in the network is periodically flooding the whole network with an originate message.
Yes.
So obviously, as this scales up, it's going to lead to quite a lot of flooded
I knew that especially
traffic.
you are going to ask this.
So obviously, there may be some optimizations to be made in choosing how often to send these messages, depending on how often it looks like the topology is changing, and whether you can trim some here because they're not important anymore. So have you looked at any ways to reduce this level of overhead?
Yeah. When I came up with this idea to the algorithm, everybody said, hey, this doesn't scale. It doesn't work and it doesn't scale. It works and it scales well. And the reason is, it's wireless. There is lots and lots of packet loss. The algorithm works according to a hot potato principle. I get a package, as soon as I can, I send it. And many are doing so. So you have an extreme high packet loss. If you would use the protocol on a wired network and set small intervals for updating information, then you will have a lot of bandwidth wasted. But actually we've seen that if you have 4 or 5 hops, then you see only a very, very tiny fraction of the packages actually. So, and the packages are very small. Our packages are at the moment 52 bytes, including all the overhead of the IP package. But the only way to convince people like you is use it. Okay, I get the mic too.
So, okay, so far we talked a lot about the algorithm, and this is the main task for Batman, the routing stuff. But unless you are a routing expert and really interested how many packets go from where to where, you're maybe more interested in all the features we also implemented in Batman, and which makes it maybe interesting for you to use it or maybe to hack it. And I think we have a lot of things to offer, which are interesting and I think not seen very often. So maybe we just jump in the next slide and then. So first of all, we created an IPC interface for Batman. That means you can connect to Batman at runtime and you can insert commands to change the behavior of Batman or to get certain information. This is done via a Unix socket. You can have multiple connections at the same time. The main purpose was that we have many debug information, and very often to get this information we had to restart the daemon to start them with a debug level. And now we just can connect and can say which debug level we want, and then it will start spitting out the debug information. Maybe go to the next slide. So we have live debugging output, and a newly added feature is that you can change your gateway settings at runtime. I will explain the settings later, but it means you can say, I want internet now, or I offer internet now, or I want another gateway, and all this without restarting Batman. We have future plans, for example, adding HNA information dynamically, or adding, I explain what it is, or we add delete interfaces for hot plugging events and similar things. Who does know what HNA messages are? One. Okay, two. Good. HNA messages are so-called announcements for networks which are not part of your Batman mesh cloud. Meaning maybe you have some kind of infrastructure, server infrastructure, and you want your mesh cloud to be able to access it. And then you announce that you have this network, and the other nodes will create routes towards this infrastructure without that you have to run Batman on this server infrastructure. Yeah, you can announce subnets or single hosts or several subnets, doesn't matter. And the idea with dynamic HNA is that you come with your notebook, normal notebook, you connect to an access point which runs an infrastructure modus, which is connected to a mesh cloud and therefore announces your notebook IP automatically in the network, so that you are accessible from the outside. Yep. So Electra already mentioned it. We have very often the problem that here's a client which wants to connect to the internet, has 2 or more gateways in range, and the connections may be equally good, and then happens what was already mentioned. We have hopping, route hopping, and the client changes the route towards the internet from one gateway to the other, which is not so bad if we hadn't net behind the gateways and all your stateful connections are lost after each hop. This can be really annoying if you have an SSH session or a zip session or anything else. It just will break down after each switch, and if you switch every 30 seconds, this becomes a funny task. So, what does Batman do? Batman offers the ability to create UDP channels automatically to the gateway. Yeah, you can go to the next slide. So, how does that work? If you have internet available and you want to share it, you just announce that you have an internet connection. You can say what your bandwidth is, and the others can see, okay, there's a 2 Mbit line, and you can say, okay, I have a client which wants to connect. You can choose between 3 modes if you want to connect. You want fast internet connection, or you want reliable internet connection, or you can set the gateway by yourself. And then the client will connect to the gateway, requests an IP for the tunnel setup, and then you can use the tunnel, and as long as the gateway is there, you can use the same gateway without changing. This also gives us a lot of possibilities. For example, we can check on the client if the gateway really has internet. Because we often have the problem that we have some people who fiddle around with their daemon and say, oh yes, I have internet, but they don't have internet, or they misconfigured something, and then all the neighbors in the neighborhood can't connect to the internet. We have a black hole. The Batman client can check if internet is available because he controls the data flow through the tunnel, and therefore we can check if internet is available. Also would be possible client authentication or encryption, dynamic encryption, but it's not implemented yet. Yeah. So also we implemented policy routing in the Batman daemon. I don't know whether this is known for everybody. This feature exists since a long time, but it's rarely used. So we use routing tables in the background to insert our own rules and our own destinations. And well, it helps to protect their own default route and prevents misconfiguration. Yeah, and even makes Batman faster because we can detect if a route is available or not and give an unreachable response back immediately. Yeah. So here's just some things put together. You can run Batman on an alias interface, meaning you can have your normal routing stuff, OSPF, OLSR or whatever, and you can test Batman next to it without changing your routing infrastructure. We have support for multiple interfaces, as already mentioned, but always with the same broadcast address. It's no problem. Electra already mentioned that Batman does not know the whole topology. In fact, the knowledge about the network is spread over the whole network. Every node knows a bit. It's a bit problematic because we like fancy graphics, we like 3D animations of our network. So we created a visualization server, which means every Batman node can send a small package to the server, and the server will gather all the packages and generate a whole topology for the network. Furthermore, we have a download superstore, which is directly connected to our source code. Every time when we commit something in our repository, we generate packages for... So for example, famous is the WRT or mesh cubes and I think IPAC and what else do we have?
We got Nokia 770, Zaurus, OpenZaurus, you mentioned it.
So we want to test it, no need to cross-compile everything, can use our packages. So, of course, we have internal profiler, memory debugger, we are very keen on optimization. And very important for us is that you don't need a very complex configuration. If you just want to use Batman, you start Batman and tell him what interface it should use, and then it runs. No need for configuration file, no need for a big knowledge in routing, just start it and it will do its job. Oh, yeah. So and here comes the interesting hacking part. We thought Batman on layer 3 IP-based routing is very interesting, but more interesting is Batman on layer 2. So we created Batman Advanced, which is a re-implementation of the Batman algorithm on layer 2. Means it works on the MAC address layer. You don't need any IPs to make it working. You can run practically all protocols on top of Batman Advanced, like DHCP, IPX, or IP version 6, or whatever you like. It does not depend on the routing daemon anymore. In this case, Batman will transport all your data to one destination or to the other. We have released the first alpha version. All the basic functions are working, as I mentioned. And we also released a set of tools, the so-called Bat tool chain, because if you want to debug your network with ping or traceroute or anything like it, you will find out with Batman Advanced that everything is one hop away. Because Batman Advanced creates a switch of your whole mesh cloud, and everything is one hop away for all layer 3 protocols and above. Therefore, we have the Batman toolchain, which is a ping, a traceroute, and anything like it for layer 2. So we can ping, traceroute, we have even TCP dump and something like it for layer 2. I think it's very interesting stuff and very new, and it's worth a look, I think. So in the future we will have multicast support, internet gateway support, performance analysis, and anything like it, but it's a very new field. There are only a few people working on that, and so we are quite lonely. And if you have ideas or think this is an interesting point you can work on, then just contact us. So, any questions up to now? It was a quick overview. Maybe we go into details in some points.
So we got 13 minutes left for your questions.
Yeah. I'm not sure I had this point for the routing algorithm. You're using statistics of the sources of various packets you receive, right? Okay.
Yes.
And but my question is that when you have to send a packet thanks to this information, do you always use the one that has the best score, or are you using some kind of probabilistic routing, which would be something like ant colonies for finding best path?
Well, the algorithm is based on the decision which is my best ranking neighbor to the destination, and best ranking at the moment means it's giving us packages quicker and more reliably than others. Yeah, well, some people say that Batman is an ant-based algorithm. There's one difference. Ants, they are routing with pheromones. An ant is working around, leaving a pheromone trace, as far as I know. And if it comes back on the same trace, it has found something, so there's a bigger trace. You will note that there's a difference in our algorithm, which is merely based on flooding. We're not sending anything back. The only traces are left in the statistics of the nodes forwarding the package.
Hi there. In the more traditional wireless setups, you take control of how you're accessing, how your security is with what you're connecting to. So you, between you and what you're connecting to, you've got some form of security set up, be it WPA, WEP, or whatever. What is the mentality on security and encryption, all this type of stuff on the mesh networking?
You mean what type of encryption you could use to secure your network? Or what?
Well, and between you and the internet, or wherever you're getting to, there's a whole heap of places where someone could be eavesdropping on you.
Yeah.
With the traditional network, you've put in place a particular level of security. It's in your control. But if there's all these other hops in between, those aren't in your control. So I was just wondering, what does the algorithm take this into account? Is there, yeah.
The algorithm itself relies on the information of others. So it's difficult to implement some kind of security. This algorithm, Batman itself, is more secure than the other algorithms because it relies less on what the others say. But in fact, you still can produce local trouble, but you cannot destroy the whole network. I mean, for example, in OLSR, you just can create a package which says, I have the best connection to all the other neighbors. And this package will be flooded through all the network, so everybody will send you their traffic. You cannot do this with Batman. You can create a local disturbance, but it will not be flooded through the network because you only send your own messages, and so the route towards you is based on the messages and not the route towards others.
Okay, but if someone's logging into their bank account and doing transactions and putting in their passwords, that type of stuff,
you still have the higher level protocols like SSL or anything else, and which is supposed to work over networks which are not reliable or insecure.
Yeah. Okay.
Well, we're basically, our main interest is community networking. So you cannot have a closed user group, you cannot have closed keys, it's just mutual aid and trust. That's the basic thing. If you want your data to be safe, yes, you have to do encryption on a higher level. Yes, and do you really trust the internet?
Okay, next question.
Pretty technical one.
Okay.
Originator messages are probably sent as broadcast?
Yes, they have to be sent as broadcast.
How do you handle the problem that unicast messages, so actual data communication, is sent with another data rate?
Yes, the algorithm is just using broadcasts to do a measurement which is just relative. This is the relatively best path. So it cannot tell you anything about the actual throughput. Yeah? And it's only broadcast, so it will not be repeated. With unicast traffic, depending on the settings of your wireless cards, it will try to get for each and every hop the data through with 7 tries, or even more, if you modify it. So it's quite good. But it's you know, this mesh routing stuff, it's a evolution. I think our protocol is a milestone in an evolution, but it's not the end. It cannot be the end, it will not be the end. What we're not doing at the moment is we're not reading from a wireless link what is the actual data speed from me to you, or to him, or to him, or to him. Of course, this could be taken into account. But we found that this generic approach of just sending and counting packets is quite generic. It could be used on our hardware zoo, because we have a huge hardware zoo in our networks. So it's quite good for this. Of course, if you do a login for a certain hardware, you can do very nice hardware-specific tricks and improve it. We are considering it, especially with Atheros, but it needs to gain more stability still in ad hoc mode.
Yeah, with a sample driver. But the last Wi-Fi SVN is pretty stable with ad hoc.
Well, I'm running ad hoc modus here on the camp, and of course this is the worst case. And yeah, the performance could be better, actually.
And another question, how far have you tested the scalability of the protocol?
This question was raised before.
Yeah, we often have this scalability questions. The main issue is what many people tend to forget is that we count on packet loss, meaning we repeat the packet, but we made tests. Just imagine after 4 times repeating, you will have only 1 or 2 packets remaining from the initial sender. So imagine the initial sender sends 30 packets, and after 3 or 4 hops, you have 1 or 2 packets remaining. Means locally you have very much information, you have very high update rate because many packets, but the more you get away from the initial sender, you have less packets and less accurate information, which is essentially what we want.
The worst case scenario for the Batman protocol is there is one node that has 1,000 neighbors, single hop neighbors. That's the worst case scenario. But usually you have at least 30% packet loss for these originator messages for each and every hop. Just multiply it, and then you see where you get. So it scales pretty well. And the biggest issue, if you compare it to OLSR, is that OLSR, this proactive approach of calculating these huge tables, if you have a number of 500 nodes in your database, calculating all routes, it takes many seconds on a small MIPS CPU. And our algorithm is just counting. So our CPU load grows linear with the number of messages that you actually get. And with the link state routing, yeah, it grows to high powers with the number of nodes. So it scales pretty well. And last word that I have to say on this, I don't believe that we can route the whole universe with ad hoc wireless. I don't believe in this. I believe we can make small autonomous zones that could be a quite big part of a city, or even some villages in a rural area. But I'm not expecting it to scale to 10,000 nodes, because the wireless layer is too fuzzy and too unreliable to do so.
So what about the realistic number of practically used nodes?
Say again, please.
How many nodes do you have had in a practical experiment?
At the moment, in Berlin, we have a network with 69 Batman instances running. Some people had more, I think. And the problem is, we have now in Berlin a huge mesh cloud, which is approximately maybe 600 nodes, but many people are just users. They are not interested in taking part in our experiments. But I still believe that we sooner or later will replace OLSR in this network. As it improves, we can still make some improvements. And after all, the people hesitate to switch to something completely new. 5 minutes, okay.
So just a few words. I think we had many problems in our network with OLSR. For example, when we reached 200 nodes, and then when we reached 300 nodes, and when we reached 400 nodes, and now we try not to grow too big in one cloud, because then our routers are busy with calculating, and we only calculate the routing tables every 9 seconds once, and we are still busy on the OpenWRT systems with OLSR. And compared to Batman, this is really enormous. And Batman does not calculate, so only counts. So the only problem we have are many packets, and so the only problem we have if we have many neighbors who sends us many packets, which is normally not the case in our scenario. So if there are no more questions, there's one.
You collect statistics from your networks and have tools to use
Yes.
those. Do you feed these statistics into simulations to see what happens when N gets bigger and bigger and see where the problems are first in trying to scale up?
Yes, we experimented with statistics. The main problem with the statistics is that we need some kind of statistic which takes into account packet loss and or arbitrary packet loss, and that makes it rather difficult to test it.
Well, we did some simulations with virtual instances, and especially to compare it with OLSR. There's always a big problem with simulations. So many people in the academic world believe in simulations. But if you want to simulate a real mesh network, even the software to do so may be more complicated than the best routing protocol ever. And you need a decent supercomputer to have a fine-grained interval where you calculate, hey, this node is transmitting and this node is transmitting. What is the interference doing? And if you try to simulate this, well, you need a decent supercomputer and a decent software. So it's better to use it in real life.
During the 1990s, the cypherpunks dreamed of large anonymous networks. And since they're anonymous, you don't even want to know who your neighbors are because you don't want them to know who you are. And we dreamed about routing protocols. One suggestion was to use Hamming distance between a node identifier, which might be the MD5 of your Ethernet MAC. And you have a stronger interest in retaining information about where nodes are whose Hamming distance is close to yours. That is the bits of your identifier and the bits of their identifier. If only a few bits are different, that makes them a kind of a neighbor of yours that you might want to remember a route to them. I was wondering if this had ever been used in practice or has gone anywheres. It might help you scale to very large numbers if everybody kind of knows who to be interested in, and through those Hamming neighborhoods you find a place to get there.
Well, at the moment, my interest is just this basic algorithm stuff. You could use our basic algorithm and pop up your extensions. So?
You mentioned the bidirectional link check that you'd added in the second version of the protocol.
The bidirectional link check.
Yeah.
Right?
So with the outgoing originating messages, you've got the statistics, building up a good statistical set for which link is most reliable coming to you. Does the bidirectional link check do the sort of same level of statistics going the other way, or is it just a quick, this looks best coming this way, and I do seem to be able to get a packet this way?
Hast du es komplett verstanden? Well, I think I didn't completely get your question or your comment. I'll just start explaining the bidirectional link check. The bidirectional link check in Batman version 3 works like this. I send my own originator message. And since wireless is a broadcast media, if you are one of my neighbors, I expect you to repeat my package. If I receive you retransmitting my package, I know that you have received me, and I know that I have received you. So there is a bidirectional link, right? As long as I make sure that the package that I see from you came directly from me. So you're not just repeating a package from somebody else. And for now 15 minutes still, that's cool. Sorry, I lost the point. Yeah, well, but that's all I have to say about it. Yeah, well, if I send a package every second, I expect you to respond in a decent amount of time with my package, with my sequence number. If it doesn't come back, I consider you as a unidirectional link in that moment when you don't respond to my package. So in this time, if you're forwarding me originator messages from distant nodes, I'm skeptical that I can use you as a link. So only in that moment when I receive that you repeat my packages, I accept you as a bidirectional link. And this has a direct influence to the statistics counted. And at the moment we are working on Batman 4. To be frank, the algorithm it routes like hell. Really good, that no looping, really nice. At the moment the metrics are not perfect. I have seen some cases when routes chosen by OLSR were better, more performant than with Batman. The inherent idea of Batman is where I receive a package, I can send to. This could lead to asymmetrical routings that are unfortunate because the way to me could be better than the way back. And we have now made some changes in Batman 4, which is the very first testing available, to make sure that the statistics are based on originator messages that come from links that I can send to better than receiving, or at least can in either directions the same quality. And this should give a very good performance boost and should also be better than OLSR at the moment, because it only uses the round trip to calculate the routes, and we are going to use the send route, the best send route as the route that we select. This should give another performance boost. Yeah. Stay tuned. Yeah, another question here?
Hi there. Just one little clarification. So I understand there that the bidirectional link isn't actually producing, or the bidirectional test isn't actually producing any more traffic on the network than normal. It's only a little bit more analysis.
Exactly.
Awesome.
It's not, yes, it's not producing any more traffic. It's nothing else. It's just the originator message that I create anyway. Yeah. I just listen if my direct neighbors are repeating them. There's no extra work to be done, no extra traffic.
And a completely unrelated question, I'm curious where you are with the visualization as someone who's also interested in this visualization stuff. I know it was much easier to do with OLSR because everyone had all the routes and every client could do a visualization, but yeah, please talk about that.
Yeah, basically, we need just one node to collect the data like OLSR does with every node. That's all we have to do. Do we have visualizations? Yes, on openmesh.net.
Yes, we have visualizations. We have, in fact, we work together with a project called S3D. It's a 3D program which can analyze the OLSR output, and our visualization server creates the same output. And we already prepared some screenshots on our website. And if you're interested, I can tell you how to use it. And well, it's quite funny and looks really good.
The visualization server of Batman is creating output similar to OLSR's network output, so you can use basically the same tools. So we are backward compatible to that. More questions? So we're due. Thank you very much.